All right. So we have integral test and P-series test. So 9.10 might help if I write theorem before that. So let's just put that up here and spell it correctly. Theorem. All right. And this is called the integral test. It says if your function f, wow, it might help if I could write today and I cannot. If f is positive, continuous, and decreasing, for all x greater than or equal to 1, and your a sub n is equal to f of some n, then you have this property. The summation as n equals 1 to infinity a sub n, which is an infinite series. And the integral, if you remember, we did how we had the 1 to infinity integrals in 9.1. So we're comparing those two things. If both those happen, you have a commonality. Either both converge or both diverge. Like there's no other way this works. So if you know based off the property, if you know the summation converges, then this converges. Like these, it's literally either or. All right. So if you know one of them, it happens with the other. So really, you only have to solve for one of them, which is kind of nice. But I guess the key thing to pay attention to is that it needs to be positive. It needs to be continuous, which, like, if it's an integral, it should be continuous, but I'm not going to get into that right now. And decreasing. So, like, you're looking for these three things. Like, you want to make sure your graph is moving downwards, left to right. So there's a couple examples of this. I'm going to talk about one of them, and then I'll talk about P-series test. So, well, my bad. Sorry. My bad.
There you go.
Give you a second to write it down. My bad. It's hard when I can't like see you all writing because I don't know when you all get done.
True. I'm not.
So take a second, and I will then talk about the example.
Wait, so, well, I guess I'll just see this when we do the example. So I'm just going to wait
Okay.
for my questions.
I'm going to do the example that will make more sense to you all because we just got done dealing with like inverse trig properties. So I'm going to do that one. It's the second example.
I'm good now.
Okay. All right. So thank you, Rocketbook. We have our example, and this is using integral test. And it says that they want you to apply the integral test. So the good thing is, if you have these problems, they're going to tell you what to do to the series. And our series is the summation as n equals 1 to infinity of 1 over n squared plus 1. All right. If you think about our trig rules from last week and doing integrals of inverse trig functions, come on, what is going on? All right. This should look familiar because you have a variable squared and what could be considered a squared because 1 squared is just 1. Which means you can determine which function that you need to be using. So it might help to label out what f of x is. F of x, or f of n, however you want to write it, is 1 over x squared plus 1 in this case. So we want to go back and kind of talk about what we're doing in 9.1, I believe. So we're going to take the integral from 1 to infinity of this value, which is going to be 1 over x squared plus 1 dx. All right, the only difference is we go through and then we say, okay, we have 1 to infinity, so we're going to do the limit as b approaches infinity, which is that concept from 9.1, of the integral 1 to b of 1 over x squared plus 1 dx. And then you integrate. So when we integrate, we're going to get limit as b approaches infinity of, well, arctan's fine. Arctan x, and that's going to go from 1 to b. Remember, arctan and tan inverse are the same. So you just split that up, and you say the limit as b approaches infinity. And you're going to get arctan, or I'm going to rewrite this. I'm going to erase that this time. I'm going to get tan inverse of b minus tan inverse of 1. I just did that so I could save myself space. And just as a reminder that these two are the same thing. All right. If you plug in infinity to tan inverse, you get pi over 2. Based off of the way the function is, that's just what happens. And if you go look at the graph, that'll make more sense if you forgot. And then anytime you have tan inverse of 1, that is pi over 4. Respectively, remember that this is like saying 90 degrees minus 45 degrees, if that helps. Like, if you need to, like, that visualization from the unit circle and you want to think about degrees more than radians, that's fine. And the good news is you're doing a half minus a quarter, so you're just going to get a quarter back. So it's just pi over 4. All right. So this series converges. All right. It's a lot of extra just to do the same thing from 9.1. Because really you're doing 9.1 over again, but they gave you a new test and you're applying the series to the integral concept. I'm pretty sure it was 9.1. Bailey, did your question get answered that you had?
It wasn't gonna be relevant to what we were doing. This was a lot different than I thought, and I'll just have to go back and look at my notes.
Okay.
So are we gonna have to do this like on homework or tests or?
This is the same thing as 9.1. So really, and like, hear me out. If you can just look at this and work through it and show that it converges, you don't have to do all this, because the property and theorem says that if this converges, then the integral converges.
Okay, so I can just do it like
right
how I was doing in 9.2 and it'll be fine.
Correct. It's just showing that if you had this type of integral that's going off to infinity for an upper bound, that they work hand in hand.
Okay.
So, like, yeah, you could go through this work. Like, maybe it's easier to do the integral than do the series. Like, that's possible. If you could show that converges, then the series converges. And vice versa.
No.
Does that make more sense?
I think so. So
it's more.
I can just do it how I was doing 9.2.
Right.
Same thing.
Right.
Okay. Sounds good to me.
I'm assuming Lily's still writing. Maybe. I don't know.
Good now.
Okay. Yay.
I'm just upset because my box is a little bit not.
Oh, it'll be okay. It's abstract art.
Yeah.
You know what? Maybe I should. No, I'm not gonna do that. All right. So then you have theorem 9.11. This is the convergence of P series.
Are are we gonna have any more examples of theorem 9.10?
No.
Okay.
Oh no, I said series and my phone thought I said Siri. That's funny. Because this I consider this theorem to be it's really this is your new information of the section. Does that make sense? So like I feel like this is what you more need to learn about, whereas like the last theorem, it's just taking a old concept and like kind of freshening it up so that way you know, okay, I can use two different things to prove convergence divergence with infinite series.
Yeah.
So the P series, and this is kind of cool. It looks similar to what you had with geometric, but no, remember with geometric you started at 0, right? So here you're starting at 1, and you have 1 over n to the power of p. So you're just going to use that. So 1 over 1 to the p, and then plus 1 over, 2 to the p, because n changes. 2 to the p plus 1 over 3 to the p plus dot, 1 over, well, it doesn't matter. We'll just keep the dot. Converges for p is greater than 1, and diverges for 0 is less than p is less than equal to 1. So basically, if it's greater than 1, you converge. If it's a fraction, you don't converge. You diverge. So this kind of goes back to that geometric idea, where if you look at a couple of examples, this is really straightforward. So, hold on, what did I write? Oh, that's a terrible question. Sorry. Interesting. All right. So they talk about this example, and they say the summation is n equals 1 to infinity of 1 over n, and then they do the example of summation n equals 1 to infinity of 1 over n squared. And you could look at this several different ways, but really you're just looking at the power that's being applied. And here you're literally just like, oh, hey, p equals 1. So the series diverges. Oh, hey, p is greater than 1. So the series converges.
Isn't
Obvious.
that n squared?
Yeah. Sorry. Yes, it is. And there's some other like little things you could see, but more often than not, that's what you're looking at. As soon as you have that power in the denominator, if you can separate it out, you'll know if it converges or diverges.
So it's the same thing as before, pretty much?
Yeah. It's just now you're looking specifically with the denominator, and you're doing n equals 1 to infinity rather than 0 to infinity. Sorry, let me move that
Okay,
over.
so what we do is we just plug in 1.
Well, you're
or
just...
n.
Well, no, you don't even have to plug in 1. You're just looking at the p-value.
That's n squared, right?
Yeah, it is. Sorry. I know I wrote it kind of
Very
small.
good.
Oh, so we look at what the little exponent is.
Yeah. So, like, for instance, here's another one. Example, summation n equals 1 to infinity of 1. Sorry, not 1. 3 over n to the 5 over 3. I mean, I could separate... I could rewrite this if I wanted to, right? I could say 3... and make that 1 over n to the 5 thirds. That doesn't really matter, but then it fits the property. The big thing is p equals 5 thirds. Is 5 thirds greater than 1?
Yeah.
Yeah, so p is greater than 1. So the series converges. So like they're super straightforward.
Okay, so we just look at the exponent and then apply the theorems from like the last thing.
Yeah.
Okay.
Yeah, super easy. That's 9.3.
Whoop whoop.
Yay.